So now that you've had some time to look more carefully at these four tables, particularly to scan them for their similarities and their fundamental differences, the first thing that I saw all groups pretty quickly agree upon are what are the elements that we know are going to have the same behavior across all four tables. The first example is the identity-like element, which we're calling E here. We agreed on that one before we left class on Friday. The other element which has the same properties across all four examples was this one that we're calling Y. And what's the reason that these Y's have the same properties as one another in these examples? So where did you find that second similarity? What is that property that all those different Y's, -1, this matrix, r to the fourth, what do those all share in common? Why did you say that those are the quote-unquote same?
All the inverse.
What are their inverses?
Of the other.
Inverse of... So, all right, so here's a question. Yeah,
If you multiply them by themselves, it gets you to the identity.
If you multiply them by themselves, it gets you to the identity. So there's an equation, y times y equals e, and again, times is to be thought of as the abstract operation. Right? When we operate on y with itself, we get back to the identity. And that's the case in all four of these different tables. So what does that tell me? It tells me something about y. What does it tell me about the inverse of y?
It's commutative.
Close.
It's itself?
It's itself.
Okay.
So all are their own inverses. All of these y's are their own inverse. After all, what does inverse mean? Inverse means something I can use to cancel y, right? When I multiply on the left or on the right. And canceling means leaving the identity behind. Right? So y operated on by its inverse is always going to give me the identity. And it just so happens that in these examples, these y elements are all their own inverses, because when I operate on those y's with themselves, I get the identity. Okay, so all those elements are their own inverses, or another way to say that is y times y equals identity. We could also use exponents. What would be another way to write that? Yeah, y squared is equal to the identity. By the way, we're going to introduce a little bit of terminology today. This first one is one we're not going to use that often. It's not a super important bit of terminology, but I kind of like the word. An element which is its own inverse is called an involution. Any element which is its own inverse is called an involution. In particular, we usually use the word involution when the element is not itself the identity, because what is identity times identity going to be? Identity, because that's what identities do, right? They leave everything unchanged. So when it operates on itself, it leaves itself unchanged. It gives me the identity. And so the identity is kind of an uninteresting example of an involution, because of course identity squared is equal to identity. But if there are other elements whose square is equal to the identity, we'll call those involutions. Okay, so where did you spend most of your time as groups working on these problems? You figured out where E belongs and where Y belongs. But then what? If you had discussions or arguments or debates in your groups, what were you trying to do? So once you agreed that the E's are all the same, the Y's are all the same, you had to figure out how the X's and Z's fell out, right? Where are the rest of the similarities going to be found? So for example, the tens group decided to label their first elements in this table E, I lost my annotation already because I hit the wrong button. So they labeled E, X, Y, Z like this, right? So they just sort of planted a flag and said, all right, we're going to call I, the element I, the complex number, we're going to call that X, and we're going to call the minus I, we're going to call Z. If you then make that decision, then the question is, for example, I don't know, over here in this table, which one of these is going to be X and which one of these is going to be Z? So how did you decide that? If you were able to fill out the rest of this table, how did you decide which of these elements over here is going to be X and which one's going to be Z? You took that X and that Z and you tested to say, all right, what happens when I multiply those by themselves? Am I getting that right? Mm-hmm. And so you figured out that X times X in this structure is I times I, and I times I is -1. And so X times X is equal to Y, which you see right here in this table, right? Then an X times an X gives me a Y. Same thing with the Z's. A Z times a Z gives me a Y. And then you look over here in the octagon symmetries, and how did you decide which one of these was going to be X and which one of those was going to be Z?
We started by just, again, putting them in order, doing X, Y, Z.
Just trying it this way?
tested the table to make sure it came out to the same answer for x times x and z times z.
Sure. R squared times R squared is going to be R to the fourth. So x times x is y. R to the sixth times R to the sixth. Let me put that off to the side here. That's R to the 12th, but then that's not one of the elements in this list. How do we know what R to the 12th actually is? Yeah, you just make that 12 into 8 plus 4. So we do a little secret Euclidean algorithm. We divide 12 by 8 and find a remainder of 4. And then what happens to that? Why does that help?
It's an octagon, so R to the 8th is the identity.
So R to the 8th is the identity. So R to the 8 plus 4 is the same as R to the 8th composed with R to the 4, and then the R to the 8th, because it's an octagon, 8 rotations by 45 degrees becomes identity. And so we end up with just R to the 4th. So indeed, z times z is equal to y. Okay. And then what choices did you make for the matrix example? Which one was x, which one was y, and which one was z? I think you had it written like this, right? X and z. And that still worked out. So one question that I'd like for your groups to think about before our next class is, did that choice matter? Did it matter which was x and which was z? And why or why not? It was x versus z. Because we could conceivably do a lot of work to try and figure out, did we make the right choice? Or maybe that choice doesn't matter. I don't know. And then there's another conspicuous blank that I've left up here. I haven't filled in the stuff for that third group. Why not? So what was the nature of the discussion you had to do to figure out G3? This is where I want to wrap up. The third one was harder because you might have decided, for example, that AB is going to play the role of my Y, the thing which is its own inverse, right? And you find out that indeed, when I take the symmetric difference of that set with itself, I get the empty set, which is our identity element. But then you also figure out that I could have made the choice that B is its own inverse. I could have made the choice that A is its own inverse. So does that choice matter, is the other question, I guess, that we have here. Does it matter which one of these we put it in? Yeah. And we find out that this is a unanimous choice. The question is how to make those details more specific. That's what you do with your groups on Slack.